Hi, I'm Jordi Ros-Giralt. I'm with the high performance networking team at Reservoir Labs. Thank you very much for having us. Actually, the heavy lifting work here has been done by my team here, and they're not able to be here, so I'm just representing my team. And but Troy and Shen are online, and they can use the chat if there are any questions that I'm not able to answer. So let's just jump into it. I'm going to be talking about enabling Suricata in the cloud using DPDK. So my talk will have two parts, basically. The first part, I'm going to be talking about the Arcore project. Arcore is a DPDK-based packet acquisition for Suricata, Zeek, IDS in general. In the second part, I'm going to be talking about deploying Suricata in the cloud using Arcore DPDK. In the Arcore project, we're going to be discussing the high-performance features, the base architecture, the hardware filtering capabilities, and I'm going to be talking also about the Arcore shared library, and the plugin layer, which, as you know, there are some developments in the Suricata community having that newer network plugin layer, basically. So then on the deployment side, I'm going to be talking about existing solutions, some of the concepts, network load balancing, and target groups. There's a specific key strategic feature which is called health check to make that work, and deployment steps and data flow and scaling, basically. Okay. So first part, Arcore. So Arcore is a vendor-independent high-performance packet forwarding engine, basically. How do we do that? So it's basically done by running on top of DPDK. So as you know, DPDK is an Intel-supported project, but you have basically two benefits when running on top of DPDK. One is the HPC features that DPDK enables. Kernel bypass, hardware acceleration. But secondly, is vendor independent. So many different NICs support that. Of course, you can run on commodity Intel NICs, but also many other vendors support that. It also has support in the cloud with Amazon with the ENA driver actually, and so on. So by running an IDS on top of DPDK, basically. You can run on a variety of environments basically seamlessly. So the architecture, as you will see, for Arcore, it has this capability to get packets from the wire all the way to the application as efficiently as possible, but also being able to forward packets across an arbitrary number of applications potentially, basically. So supporting Suricata, Zeek, and tcpdump and tap interfaces for more general purpose connection, basically there. So in terms of the Suricata integration, it's based on the workers run mode, so it supports multi-threaded workers for scalability. It has an easy configuration through the Suricata YAML. Arcore itself provides a YAML file to configure. So it's integrated with the Suricata stats counters, basically. So it's using the the callback function that Suricata provides to provide the counters from the lower layer, basically. Let's talk a little bit about the HPC optimizations. Provides kernel bypass, typically from DPDK applications. Zero packet copy, so end-to-end zero packet copy. That's very important for performance. The design is carefully done so that it's lockless. A packet goes from the wire to the sensor or to your application without traversing a log, basically. That's also important for efficiency, avoiding memory contention. It has hardware accelerated packet shunting, basically, so we can leverage the DPDK RTE flow API. Or also, you can do that in software, so there's a software way to do packet shunting. Then supports NUMA affinity, that can be configured through the YAML. CPU core affinity as well, so you can map your cores to your processes and threads to the right core, also through the YAML. That enables multi-core elastic scalability, if you will. And then, the optimizations that we implement, there's a couple of papers at SC, supercomputing papers that you can download and check it out, basically, on some of the optimizations that are implemented in our core, basically. So that's for HPC. In terms of the architecture, so basically, there is an R core controller. So I think there is a discussion in the Suricata community about some DPDK development, and there's a discussion about using a merge versus a split approach. In DPDK, there is this notion of primary versus secondary application, and I'm going to talk about that in a couple of slides. But basically, our core is based on a split approach, basically. So it it has a controller that sets up threads. Multiple threads, what we call the forwarders. These forwarders, we get packets from the rings, from the hardware rings, and then push them into application queues. And then Suricata runs in a separate context in its own processes, so it's and it's just reading from there, basically. So that keeps the architecture sort of clean and separation of concerns and so on. So yeah, so that's why we have an R core controller on this side, basically. The R core controller is responsible for setting up the forwarders and configuring the packet forwarding engine. We expose a CLI called R core net util that allows us to basically configure and manage, turn on, turn off R core. And then we have plugins, additional plugins that you can connect to Zeek, SuriCata, or tcpdump, or we also enable tap interfaces, basically. And also we can filter traffic based on DPDK RT flow and also software BPF, basically. So just to zoom into that diagram a little bit more legible, if you will. Again, there's on this side is sort of the control plane, the R core controller, the CLI, and this is sort of I'm actually going to use this a little bit more. Yeah. And on this side, you have incoming traffic, that's your data plane. You have the forwarding engines, that's where your threads, your forwarder threads would be running. They're mapped, they are typically pinned to their own cores to make sure that they're not disturbed. And then packets are being forwarded to your applications, whether it's Zeek, SuriCata, tcpdump, or tap, and it's done in a zero copy. So basically, there's reference counters and packets get cloned, basically. So digging a little bit more into the architecture from left to right. So that's where packets coming in on this side. That's this could be your NIC port, whether it's a VNIC or physical NIC. Then you have rings, hardware rings, basically. So this the NIC would DMA your packets to the rings, and it would be doing that based on hashing the IP tuple in the packet, so that your traffic is balanced across the rings. That's done in hardware, so there is no involvement of the CPU. But at this point, then you have forwarders that actually are reading the packets from these rings as fast as possible. They are dedicated forwarders. And then what they do simply is their mission is basically to remove or the packets from the queue as fast as possible to make sure that there are no packet drafts on the incoming traffic. So remove them from that queue and put it in a software queue, basically, sort of on this side, where they can be read from Zeek or SuriCata or a tap interface, basically. And this is the design that is basically meant to be, or is designed for lockless. So there is no locking here, and the way this is done, in order to ensure there is no locking, there's some kind of equations here that define, the fan out and fan in. Not all possible fan outs and fan ins are possible to achieve lockless. Think about the basically the problem of multiple readers, multiple writers. So not all combinations can be done lockless, and so in order to ensure lockless, there are some equations here sort of that you need to satisfy in terms of how many rings you can have versus how many forwarders and versus how many workers. But in general, it gives you enough degrees of freedom that you can actually compose the configuration that will fit well in terms of the balance, performance versus overhead. Making sure that you don't use too many cores for the forwarders because you want to have plenty for your application and so on. So in general, you have plenty of flexibility to achieve lockless, the lockless data flow, basically. Yeah, so I mentioned the capability of hardware filtering. That's typically an important one. And also, when you're talking about DPDK applications, you want to make sure you leverage that nice roadmap on the physical side, which enables some acceleration, like, for instance, typically filtering. So, yeah, the architecture here is, you can set filters. So there's an option in the CLI. There's a method called setFilter, and you can pass basically a filter. And you can do that at two levels. You can set up a software filter or a hardware filter. The hardware filter would go down to the NIC and deploy it on the DPDK NIC. And then that's using the DPDK RTE flow, basically. So it's a vendor independent in that sense. And then if it's a software filter, then you can do it using BPF, and you can deploy that on a per application. One thing is that the hardware filter would be global, sort of global for all applications at that point. But the software filter, you can do it on a per application basis. So it gives you a little more granularity there, but of course at the penalty of using software for that. Examples of hardware filtering, flow shunting, dropping flows that you no longer need, or maybe dropping the tails of flows once you have already analyzed the head of the flow. Flow forwarding and tunnel decapsulation. In some cases, like in the cloud, you have a VXLAN tunnel, so you may want to do decapsulation on the fly. And if the hardware supports that capability, then that's nice because you don't have to do anything on the software side. Of course, not all hardware supports all these capabilities. So that's again, that is vendor specific in terms of what capabilities. The RTE flow is generic, but then you have to check whether the specific NIC you're using supports that, basically. Yeah, in terms of the life cycle, continue to work our way through here in the architecture and sort of some of the concepts. The life cycle of a packet, and this incorporates the notion of memory management, if you will. So again, data flowing from the left to the right, and what you have, you have a NIC or a VNIC, DMA's packet to the RSS rings, and that's done based on, as I mentioned, based on the hashing. So there are 2-tuple hashing or 4-tuple hashing, whether you include the layer 4 hashing or not. And then at that point, you already have your traffic balanced onto multiple rings, and then you have forwarders reading from the string. This is the call on the DPDK side. For those familiar with DPDK, it's you receive packets in bursts typically, so you coalesce multiple packets in order to ensure you avoid sort of too much overhead. You don't call that on a per packet basis, so you sort of pull as many packets as you can from, and then you enqueue them. You enqueue them to the application queues. These are implemented as part of RCore, and then when RCore exposes an API, then the upper layer application, SuriCata in this case, can invoke. And this is RCoreNet get PCAP packet. It's very similar to a PCAP API, basically, here at this point. And so this is where we interface with SuriCata. So SuriCata would call this function here to get packets. And then once it's done with the packet, then of course then there is the deallocation process. Then there is the mbuff pool. Mbuff stands for basically a packet structure, and then you allocate it back, and then you sort of refill the RSS rings for more packets to be DMA'd into those mbuffs, basically. So that's sort of the life cycle. And as mentioned, one of the things is that when you have multiple applications and in zero copy, when you deallocate, it doesn't mean that you're going to be deallocating at that time. There's a reference counter, so and basically that's how you achieve sort of zero copy there, because the mbuffs are basically shared across the multiple applications if you're running multiple of them. Yeah, so one of the features I guess we provide in our core is ease of use, if you will. So everything is configured through a YAML. You can also configure some of these things through the CLI, but the YAML is the entry point. You have your deployment, so you configure your YAML, and then that's how you can recreate that over and over, basically. So I'm going to highlight some of the fields in the YAML, basically. There is the capability to set up how many forwarders. These are the threads that read packets from the hardware rings, basically. In this case, so we set up 4 forwarders. In some cases, 1 forwarder is enough. In some cases, but if you are really handling a lot of throughput, then you might want to bump up that number. Forwarders are just doing, getting packets from one ring and putting them in another ring, basically, into the application ring. Number of rings. These are number of physical rings, or the hardware rings at the lower level. So packets coming in would be DMA'd into 8 rings in this case. The ring size, that's how many packets you can each ring can host, basically. And then the worker queue size, that's the queue size at the upper layer that interfaces with Suricata. That's the number of queues. Then here you will see that we have the port section of the YAML, and here's where we define some of the elements here for each port. We define the cores that we pin. So this has to be in agreement. So remember, there are 4 forwarders. So, and we have 2 ports. So if you want to use pinning, which is an option, I mean, you can that's optional. But if you want to pin the forwarders, then you have to specify which core to pin them on, basically. And so because there are 4 forwarders, you want to make sure that you allocate 2 for each port, basically. And this is the core ID, 1 and 2, 14 and 15. You may wonder, how do I know these core numbers? So when you launch our core, the controller, it's going to look at your processor, and it's going to make a recommendation on which cores you can use that are available, and then you can use that. So basically, I'll show you in the next slide an example of recommendation from the controller. On the application side, then similar. Basically, you can name the application, whether it's Suricata or Zeek. That's the human name, basically, sort of human readable name that you can. It's just for you to know which application, and then again, how many workers. So that's a worker count. So here we're allocating 4 workers for the application for Suricata. And this is running also Zeek in parallel, so it's allocating 8. Typically, Zeek is a little bit more demanding. Of course, depends on how many rules you deploy, but and so you might want to allocate a little bit more. And then you can see that also this configuration actually sets up a tab interface, which is the type is called tunnel, basically. So you would actually be able to plug another application, an arbitrary application, on that tab interface. It's a slower. That's not the high performance, because that goes through a kernel, for Linux kernel. But it's good for debugging or visibility. And you may want to put a filter there and maybe just look at some of the packets that are coming in, and so on. Yeah, that's like I mentioned. The controller makes you recommendations once you deploy. Once you run the controller, it's going to create forwarders, and then it's going to give you recommendations on how to pin the application in this case. And yeah, I think before I was talking about the forwarders, but actually it's on the applications that the recommendations come up, basically. So there's this option, this method called getInfo, that's going to give you, among other things, the recommendation. So this is telling you, you want to run 4 Suricata workers, so it's recommending to use Node 0, Core 7, and so on and so forth. So basically then, once you have deployed the controller, you can then run Suricata, and then based on this mapping, say. So you could even instrument that basically on a script and do that automatically, basically. Okay, so that's pretty much sort of the architecture. couple of points we wanted to connect with the community here. It's the recent developments on the Suricata side. So our core today runs as a shared library, and so it uses DLOpen basically to load the library, and then we have a patch basically, and we maintain that patch basically. But there is this very nice development that provides basically a plugin capability, dynamically loadable plugin. So here are the pointers of the conversation and the pull request. The pull request I think came a couple of months ago, so it's very recent. But the conversation has been going on for more than a year. And actually, no, that's on the DPDK side. Sorry, this one might be the timings might be a little bit different. But yeah, you see the example here basically. So the init plugin, and when you initialize your plugin, it's gonna call DLOpen to basically load your library. Here you would pass the path to your library. So that's the typical way to sort of load DLOpen. We do something very similar today. It's just that we're using a patch. It would be really nice. And that's our sort of next step to basically, move into that direction of using what the Suricata stack provides in terms of the loadable plugin. The other connection with the community is this this effort that DPIN has initiated support DPDK for Suricata, and this is the conversation actually that initiated more than a year ago, and very interesting. And that's where there are these conversations around merge versus split mode. As I mentioned, our core is a split mode, so it has the primary and secondary, and then Suricata runs on the secondary. The controller and the threads are the primary, and then a couple months ago there was this pull request basically, and we think this is a very interesting development, and look forward to comparing nodes basically on this regard and finding synergies in this area. Okay, so that's the first part. Second part, I'll try to cruise, but basically it's how do we run this in the cloud and then sort of achieve some level of scalability, basically. So, there are out-of-the-box Suricata cloud deployments. I'm sure you've seen them. They're starting to come up. You can search it on AWS, on Microsoft. A lot of these things are moving pieces. Some of the things that it's not clear what's supported. Does Microsoft support traffic mirroring? It seems like now it's being called, but in some cases, like AWS has a traffic mirroring capability, and the field is moving very rapidly, and so you can go online and sort of check some of these user guides and deploy Suricata in the cloud. My conversation is going to be on specifically how to deploy it using DPDK, and we enable that through our core basically. So you get the benefit of performance in this case. It's leveraging the ENA interface from AWS basically, so you get the better performance and some of the capabilities that are offered by leveraging the our core project basically. A couple of simple concepts to set the stage. One is the notion of load balancing, and the other is target group basically. So this is mostly AWS terminology, but it's fairly generic basically. So what we want when you run in the cloud, you want some notion also, if you're aiming for some kind of scalability, basically be able to optimize your OpEx, right? You don't want to have too many instances running, or that you're wasting resources, and you don't want to have too few instances that you're dropping packets. So that is going to require some kind of flexibility and being able to do this dynamically and so on. So there's this notion of load balancer that's implemented it's available from AWS Cloud. Specifically, there are different kinds of load balancers. We're using a network load balancer, which is one kind. And then there's a notion of target group. A target group is where you register your instances, and these instances is where you would run Suricata on top of DPDK, basically. So what you do is you register new instances, you launch them inside a target group, and then you associate that target group with the elastic load balancer, the NLB, and so that's the NLB is being associated with this target group. It's going to know basically where to forward the packets, where to do the load balancing. There is one key feature to enable this workflow, which is how does the NLB know that an instance is alive, basically, or that the instance is actually available to handle traffic. And that's where this capability of health check comes in, basically. And that's also part of the cloud, so the AWS provides a health check capability. So the NLB can sends a health check probe to the instance, and then it waits for a response. If there is no response, it's going to assume that that instance is not there, and so it's not going to forward traffic to that instance, right? So there are different ways. It supports different kinds of probes. One of the commonly used ones is TCP. It's just a three-way handshake. It's a data-less TCP connection, if you will. Just the three-way handshake. It's being used to check if the instance is alive, and it also supports ICMP probing. But the key element here is that because typically IDSs are really passive, right? They are not an active server. They don't. They receive packets and they are not attached to a TCP/IP stack, if you will. And so the question is, how do you handle sort of a three-way handshake which relies on the TCP/IP stack on a software stack that actually is not bound to a TCP/IP stack itself? So imagine this packet is actually coming into the NIC. This NIC goes through DPDK. It's bypassing the Linux kernel and going all the way to Suricata, right? So there is no TCP/IP stack. So who's going to respond to that three-way handshake? So that capability is implemented as part of RCore. So RCore implements a small mini TCP/IP state machine enough to allow for this handshake to succeed. So it does things like turning around the packet, basically swapping IP addresses and recomputing the checksum. And then, of course, it has to enable the DPDK transmit path. So before this capability, we only had the receive path. That was enough. But now it also has to enable the transmit path, basically. So that's how we can support health check, which is sort of a strategic capability to enable scaling in the cloud, basically from that regard. Yeah, so that's the YAML part for the health check capability. So it has different modes. 0 is disable, 1 is for TCP ICMP, and 2 it's just for ICMP. And one of the things that this does is basically, okay. So one of the challenges when we're doing health check is that you have gigabits of traffic coming in. And then you're looking for a single packet that's just a probe. It's like finding a needle in a haystack, right? In a haystack. So, when we're handling the traffic, one of the advantages of using DPDK is that we don't have to load the packet into the cache. Basically, we rely on the hashing information provided by the hardware. So all we do is we look at the hashing value, and then RCore knows how to forward that packet. So it doesn't need to look at the TCP/IP header, actually. That's important because if every forwarder had to look at the TCP/IP header, you would have to load the packet into the cache, and that's expensive. What we want is that only Suricata should load the packet. Of course, somebody has to do that once, for sure, because we need to inspect that TCP/IP header, but we only want to do it once. And we want just Suricata to do that. We don't want the forward to load that, and then Suricata do that again, and so in that case, that's just how it works. But the health check forces us to look for this TCP header. So just because we need to support health check, then it means that we have to look for every single packet. We have to sort of load the packet header on the forwarder side, and that has a penalty hit. We did some benchmarks. It's not huge, but it has some penalty hit. Now the question is, can we use DPDK hardware to actually figure that out? And that's this capability here. Today, unfortunately, some of the capabilities are still work in progress on the DPDK roadmap. This is probably going to come soon that we're going to be able to do the same on TCP handshake. But for ICMP, we can do this capability from by the hardware telling us this is an ICMP header, and then you don't have to figure that out yourself on the software side. So that's one of the elements there. Yeah, and that's some of the capabilities here that you can sort of check. I'll probably you can configure some pre-upgrade wait time. Like sometimes you don't want to switch to an unhealthy state immediately. You want to wait a little bit, and there are some capabilities. You can also whitelist the IP address that you want to listen from, and so on. Okay, then we have a way to get the stats from our core. So you get the stats on all kinds of counters and everything, both human readable and also in JSON format. This portion here shows the health check probes. So this is telling us that this instance of our core got 10 probes, and 10 of them were acknowledged. So that means that 10 times we say we're healthy. It also counts foreign probes. If you have IP whitelisting, that a foreign probe is basically you get a probe from an NLB that has a different IP address than the one you think you should be looking at. So so that's some of the stats. So how do we deploy this in the cloud? I'll keep this at a very high level, but there are different ways, of course, as you know, and I'm picking here on AWS case, basically, but you can do this through the management console, through the CLI. You can use CloudFormation and create a template, or you can use the cloud development kit as well. So that's different ways to do it. From if you really want to sort of do this programmatically, CDK gives you the richer set of capabilities. You can script this, and if you just want to do this manually, you can use the management console, depending on at which level you want to work. The deployment steps also keep them at a high level. So number one, you start with the VPC in the cloud. So where you have traffic that you want to observe. So maybe you have instances that you're trying to monitor. Then number two, you create your SuriCata instances. So you have, again, two kinds of instances. One's the ones you're trying to monitor, and the instances where you're running the sensor, the SuriCata sensor. And then you create an NLB to connect both, basically. And then, as mentioned before, you have to create a target group where you register your targets, basically the SuriCata. So the SuriCata instances belong to the target group, and then you associate the target group with the NLB. So at that point, the NLB knows that there are these instances that it needs to forward traffic to, and it's going to run the health check protocol to ensure that they are alive. Then you create traffic mirror sessions, so you mirror the traffic from the instances that you're trying to monitor, and you configure the traffic mirror to forward the traffic to the NLB, to the network load balancer. Typically, then what the cloud does there is create a tunnel, and it's going to be using VXLAN and forward that traffic to the NLB. So the VXLAN encapsulated mirror traffic will now flow from the traffic mirror to the NLB, and then from the NLB is going to be sent to the SuriCata instances in a load balance fashion. Then the health probes basically are running in the background, monitoring if the instances are alive and so on. So that's how you could sort of deploy your instances. That's end-to-end data flow. Basically, start again from the left to the right. You have your monitor instances. We mirror them. We mirror their traffic. The target of the mirror is the network, the NLB, which then load balances the traffic against a set of SuriCata instances. So, and here you have your traffic, which is a mix of health probes and your VXLAN traffic, basically. And so, okay, that's all good. Now, how do you sort of achieve some level of elasticity in this architecture? And so, just to conclude here, basically, what you can overlay on top of this data flow is this notion of monitoring whether your instances, your hardcore Suricata instances are alive, for one, and also whether they are keeping up with traffic. Suppose that they're starting to drop traffic. So you want to, if they're starting dropping traffic, you want to add more Suricata instances, right? So this is again a use case based on AWS. What you can do in this case, you can program a CloudWatch alarm that just monitors the NLB metrics. The NLB reports CloudWatch metrics. Specifically, can report when it senses that one of the hardcore instances is unhealthy. Then it's going to flag that. That's going to create an alarm. You can configure this alarm to send an SNS notification, basically, which goes to through a publishing through the publisher, and publishes that in a topic. You can then configure an AWS Lambda function to read from that topic, and then in this function, that's where you can add the logic to launch a new instance, a new Suricata instance that you would then register in that target group. Once you register that in your target group, the NLB automatically is going to be able to see that there is a new instance and start probing that instance for health, for a healthy state. And then if it's a healthy state, it's going to be able to forward traffic to that. So that gives you a sense of how, from a rigid deployment, you can add on top this sort of monitoring here, and then be able to react when the system, when one of the instances goes down, basically, or is dropping packets. So that's really what I wanted to describe today, and I don't know if there are any questions.
Okay, are you ready to breathe? I'm not